Up till now in this chapter, we've discussed the nucleus and we've talked about how protons and neutrons are found in the nucleus, but we haven't really discussed electrons and where electrons are. Now, we know that they are outside of the nucleus, but we're going to get into even more detail as to where electrons are actually located outside of the nucleus of an atom. And in order for us to understand where electrons are, and where they're located outside of the nucleus, we actually have to study electromagnetic radiation first. And back when we were talking about nuclear radiation earlier on in this chapter, we talked about things like X-rays and gamma rays, and those are a part of the electromagnetic spectrum. But the electromagnetic spectrum is bigger than that, and you can see it down here. So we've already talked about gamma rays and X-rays when we discussed nuclear chemistry. But you also need to know about things like radio waves, also microwaves, and those are the same kind of microwaves used in your microwave oven. Then we have infrared electromagnetic radiation. Then we have ultraviolet. And you can see that there's this very narrow band here, and it's actually even more narrow than this. I mean, this is not to scale, which is the visible portion of the spectrum, and this is the part that can be seen with the naked eye. And you can see here that on this diagram, we have frequency, we have wavelength, and what I'm going to do is I'm going to explain wavelength and frequency, and I'm going to discuss with you how that relates to energy. So let's start with wavelength. And wavelength is the distance between any given point and the same point in the next wave. So let's say you have something like this. Okay, I'll just make like a little y and x axis like this. Let's say you have a wave and the wave goes up and down, and I'm just doing my best here to sketch a wave, okay? So a wavelength is the distance between any two identical or successive points on a wave. So if we pick, let's say, this point here, so then we go up, then we go down, and we're going back up, okay? And so this distance, okay, the distance between these two successive points, that would be a wavelength, okay? That would be a wavelength. And it's not discussed in our textbook, but the Greek symbol that's used for wavelength is the letter lambda. Anyhow, so lambda is used for wavelength. And then frequency, if I just zoom out here a little bit, frequency is the number of waves that pass a fixed point per unit of time. So if we have a unit of time, so let's say maybe this is 1 second, okay? This is 1 second of time. So you see that this wave, you have one wavelength that I have highlighted in red, and let's say I highlight a second wavelength in green, starting here, like that. So that would mean you have 2 wavelengths per second, so it has the frequency of 2 waves per second. But let's say I had a wave like this, let's say you had something that's like this, okay, something like that, okay? Now you can see we've got 1, 2, 3, 4 waves per second. So you'd say the black wave has a higher frequency, right? There's more waves that pass that fixed point per unit time. And when it comes to energy, okay, I want you to understand how energy relates to wavelength and frequency, because it's kind of interesting. It might be a knee-jerk reaction to think, well, the long waves, the big waves, those should be the most energetic, but they're actually the lowest energy waves. So we're going to put down here low energy. And the waves that have a short wavelength, okay, things like gamma rays or ultraviolet radiation, right? Those are actually high energy. So high energy up here, okay? So to repeat, if you have a long wavelength, it's going to be a low energy wave. If you have a short wavelength, it's going to be high energy. And you can see that energy is also directly proportional to frequency. You can see that if this is frequency up here, you see the higher the frequency, the higher the energy, the lower the energy, the lower the frequency. So again, the only part that is inversely proportional to energy is going to be wavelength. Big wavelength, low energy, short wavelength, high energy. Now at this point you might be asking yourself, okay, well, why do I have to study light? I thought this section was on electrons. Well, in order for scientists to understand where electrons are actually found outside of the nucleus, they use light to probe the atom and to figure out where the electrons are. So check this out. It says particular wavelengths and frequencies relate to different energies. I just told you that wavelength is inversely proportional to energy and frequency is directly proportional to energy. So again, higher frequency and shorter wavelength are the most energetic, okay? You could say energy is directly proportional to frequency, okay? Or you could say energy is inversely proportional to wavelength. I'll just put lambda like that because I told you the Greek letter lambda is used for wavelength. It says here, the discovery that energy was quantized, quantized just means it can only exist in fixed amounts, was inconsistent with Rutherford's model of the atom. So if you remember Ernest Rutherford, he just thought that electrons could be anywhere outside of the nucleus. He says they're just moving around, they could be anywhere. But it turns out that's not true, and it was a Danish scientist by the name of Niels Bohr who developed this model where he figured out that electrons are actually confined into clearly defined energy levels spaced at specific distances away from the nucleus. So there's a lot to unpack here. So let's go over the word quantized first, okay? Because quantized says can only exist in fixed amounts. So what that means is if we have an atom, okay, and what they're showing here is a neon atom, you see there's electrons outside of the nucleus, right? Here's our nucleus, and then we have all these electrons, outside. But you see how they only exist in these particular circles, okay? And I'm going to call these orbits, okay? There's no such thing as an orbit. We know that now, but this is, again, Niels Bohr model. You see this circle here? That would be considered an orbit. So we said electrons can exist there, and they can exist here in this higher orbit, this one that's larger, okay? And the idea is that the electron cannot exist in between. So in between these two lines, no electrons can exist there. That's what quantized means. It can only be in one energy level or the other. It can't be in between the two. And so, again, that was one of Niels Bohr's largest contributions to our current understanding of the atom. Now, of course, we've moved on from this. We've moved past the Bohr model, but this is an important stepping stone, understanding that electrons can only exist in specific distances from the nucleus. They can't just be anywhere. They have to be at specific energy levels, and that's what quantized means. It means it can only be at a specific energy level. And so to give some more detail on the Bohr model, it says here that in the Niels Bohr, or the Bohr model, electrons can climb up or down the energy levels almost like the rungs of a ladder, but the electrons can't just move freely anywhere, okay? They can't just be anywhere outside of the nucleus. They have to be in specific energy levels. And you can see here, we have our nucleus right here, and then we have these specific energy levels. There's one here, then we have another one, and another one like that. And we call those specific energy levels, we call those shells, okay? So a shell gives you the location and energy of electrons around a nucleus, and it's designated by a value of n, where n is just an integer, 1, 2, 3, 4, 5, 6, so on and so forth. So if I zoom in here, okay, this first energy level here, this would be n is equal to 1, n is equal to 1, this one would be n is equal to 2, this would be n is equal to 3, this would be n is equal to 4. You probably noticed that the lines are getting closer together as we get further away from the nucleus, which is true, but our textbook doesn't go into any detail on that. But we have these energy levels, and so the n is equal to 1 energy level is going to be the lowest energy. Okay, so n is equal to 1 energy level or shell is the lowest energy, and it's the closest to the nucleus, and it's attracted to the nucleus, okay? N is equal to 1. Again, I don't think this is in your textbook, but oftentimes this is referred to as the ground state, the lowest energy level, the ground state, if you want to know. And so electrons become higher in energy as they move away from the nucleus. So let's say, and just let me zoom in here, let's say you have an electron right here, okay, this red electron here. You can see that if it absorbs energy, it can go to a higher energy level. But then, what goes up must come down. And so if you have an electron at a higher energy level, like n is equal to 2, as is shown here, it can go back down to n is equal to 1, but it's going to release energy. Okay, and that energy that's released is in the form of electromagnetic radiation or light. Okay, and so what scientists did is they would subject different types of elements, or different elements, I should say, to energy, And then what would happen is that the elements would emit light, and then they could just see what kind of light was coming out of the atom. And that's how they discovered the different energy levels. Okay, and I'm just kind of really skimming over the surface here, but this is what we need to know. Now, besides the energy level, n is equal to 1, n is equal to 2, n is equal to 3, we can actually be more specific about where electrons reside in an atom because each shell contains one or more subshells. So we have our shell, okay, so let's review. We have our shell, which is our n is equal to 1 or 2 or 3, etc. But then we have a subshell, okay? A subshell, and it says each subshell consists of one or more atomic orbitals. So that way we can precisely locate an electron by its shell, subshell, and orbital. Now if you're like, why do I need so many descriptors of where an electron is? Well, first of all, electrons are... The reason we spend so much time discussing electrons in chemistry is because electrons are what are involved in bonding, okay? And if you're getting excited in this course and saying, when do we get to the A plus B gives me C? And when do I learn how to make, a new chemical compound? When do I learn how to make a molecule? Well, in order for you to understand how to make molecules, like maybe a life-saving drug, you have to understand electrons thoroughly because electrons are involved in bonding. Now, furthermore, if you were to go to, let's say, a sporting event, okay? Let's say you went to go watch the Denver Nuggets play basketball, okay? They give you a ticket. It's not just going to have one number on it, right? It's going to say you have a section, you have a row, and you have a seat. And that's kind of what we're doing here when we provide the shell, the subshell, and the orbital. That way we can provide a precise location for each electron of an atom. Now the subshell, which is the subdivision of a shell, is designated by a letter, which is S, P, or D. And there's actually a fourth letter, which we don't get into in this class. But in case you're the kind of person who likes to research everything that we cover in this class, and you're like, what about F? Isn't there an F orbital? There is an F orbital, but we're not going to get into F in detail. But what you should know is that the subshells increase in energy. So S is the lowest energy subshell. It's lower energy than P, which is lower energy than D. So D is going to be higher in energy than P, and P is going to be higher in energy than S. And then again, in this class, we're not going to worry about F orbitals, but F orbitals are actually higher in energy than SP or D. So if you're like, what's an orbital? I heard you talk about an orbit, which was, that circle that was around the atom. So if I just back up here a little bit, so just permit me, okay? Remember, this model here was developed by Niels Bohr. This is the Bohr model where you have these electrons orbiting around the nucleus. So we called those orbits, but now we've moved on thanks to somebody named Erwin Schrödinger, okay? And we've come up with a more modern understanding of the atom, and that is that electrons don't actually orbit the nucleus. They reside in what we call orbitals outside of the nucleus. And an orbital isn't just some kind of, circle that the electron can move in around the nucleus. It's actually a three-dimensional volume of space around an atomic nucleus in which electrons of the same energy may reside at any given time. Groups of orbitals with the same n value form subshells. Each orbital can hold 2 electrons. So here are the different types of atomic orbitals. Now, again, there is an F orbital, which isn't shown here, but you don't have to worry about that in this class. The first one is the S orbital. A lot of my students remember this S for sphere, okay? It's spherically shaped, okay? Then we have the P. The P orbital kind of looks like a peanut maybe, or a dumbbell or something like that. A lot of times my students like to describe it as a dumbbell, so we can put here dumbbell. Okay, and the d orbital just looks like 2 p orbitals that are crossed like this. And so what the expectation is, again, is that you understand that s orbitals are lower in energy than p orbitals are lower energy than d, and you should be able to recognize them. So let's say I just showed you a picture of this. You should be able to say that's a p orbital. Or let's just say I showed you just this. You should be able to say that's a d orbital. So just recognize what the orbitals look like. And so in any one of these orbitals, these types of orbitals, remember that any orbital can hold 2 electrons, okay? So every orbital can hold 2 electrons. So if you have a specific S orbital, it can hold 2 electrons. If you have a p orbital, it can hold 2 electrons. If you have a d orbital, it can hold 2 electrons. However, there's 3 types of p orbitals and there's 5 types of d orbitals, okay? And I'll get into that in more detail in just a minute. So let's take a look at the relationships between shells, subshells, orbitals, and electrons, okay? So we have our shell. So we have our n is equal to 1, 2, 3, okay? And then it can keep going. So number of subshells in shell. Okay, well, this is kind of interesting. So we notice that these two are equal to each other, okay? And you remember that the subshells, like I told you, they go S and then P and then D. So if we only have one type of subshell, right, and these are subshells, SPD, and of course there's an F that we don't discuss in this class, that means that the only subshell that we could have would have to be a 1s, right? Because first we put the shell number and then we put the subshell after. But once you get to 2, since there's 2 subshells, well, first you're going to pick the lowest energy one, and then you're going to pick the one that's next to it, the next highest in energy. So you have a 2s and a 2p. Then when you get to 3, well, you're going to have a 3s, a 3p, and a 3d. Now, if we go from the subshell designation to the number of orbitals in a shell, okay, remember, I told you that when it comes to S, there's 1 type of orbital. When it comes to P, there's 3 types of orbitals. And when there's D, there's 5 types of orbitals. So if we have a 1s, well, there's only an s, so there's only 1 type of orbital. Then if we have a 2s, again, an s only has 1 type of orbital, and so we have 1 type of orbital here, or 1 orbital, excuse me. Then if we go to 2p, well, I told you that there's 3 types of p orbitals, so we have 3, okay? Then for n is equal to 3, we have the 3s, the 3p, the 3d, and so the number of orbitals in the subshell is 1, 3, and 5 respectively. And you need to remember or memorize these numbers. There's 1 type of s orbital, there's 3 types of p orbitals, there's 5 types of d orbitals. Now, how many electrons did I say you could put in a subshell? I told you that you could always put 2 electrons in a subshell. So if we have 1 orbital, that means we can have a maximum number of 2 electrons. If we have 1 orbital, a maximum of 2. But then once we get to 3, right, like a p orbital, well, there's three orbitals. Each one can hold 2 electrons, so that gives us 6, okay? So you can see that when we get to n is equal to 3, we have the 3s, the 3p, and the 3d. So we have 1, 3, and 5 orbitals in our subshells, respectively. So each one can hold 2. So really all you're doing is just multiplying by 2, multiplying by 2, multiplying by 2. So we have 2, 6, and 10 electrons, respectively, for our 3s, 3p, and 3d subshells. So now, if we tally up the maximum number of electrons in a shell, you can see that for a 1s, or maybe I should just say, for n is equal to 1, you can have a maximum of 1. For n is equal to 2, you can have a maximum of 8. And for n is equal to 3, you can have a maximum of 18. Now, there is a formula that can be used to calculate the maximum number of electrons in a shell. So if you go from shell number to maximum number of electrons in a shell, the formula is 2 times n squared. So you can see that if you go from 1 to 2, right? 1 squared is 1 times 2 gives you 2. If you go to 2, 2 squared is 4. 4 times 2 is 8. And if you go to 3, 3 squared is 9. 9 times 2 is what? 18. So you can use this formula. I don't ask my students to use it or anything, but if you're the kind of person who likes patterns and formulas, you might find that handy. As I was saying just a couple of minutes ago, why do we spend so much time talking about electrons in chemistry? In fact, if you take organic chemistry, which you're going to in the second half of this class, I mean, organic chemistry, the only thing you talk about are electrons. And so electrons, why are they so important? It's because they're largely responsible for the fundamental properties of atoms and the interactions of atoms with one another. And one type of interaction would be bonding, and reactions. Okay, so if you're interested in bonding and reactions, which I sure am, you have to understand electrons. And so like I said, understanding the arrangement of electrons in their shells, subshells, and orbitals is critical to recognizing where the electrons reside in the atom. And so a way that we can display electrons, or the way electrons are organized for an atom or an ion, is using what are called electron configurations. And these are a detailed arrangement of the electrons indicated by specific notation like 1s2, 2s2, 2p4. And so what we're indicating with the number is the energy level, right? This is your N, okay? Then we have the S, which is the type of subshell in this example, okay? And it could be P or D or F, but again, we don't really cover those in this class. And then the superscript here, this represents the number of electrons in the subshell. So what they're saying is that in this 1s orbital, we have 1 electron. Now, how many electrons can you have in an s orbital? Well, there's only one type of s orbital, and it can hold 2 electrons. And so after 1s2, then it would be full, so then you'd have to go to the next highest n, which would be 2. So then you'd have to go to 2s, and then you'd have to go to 2p, right? Because I told you the s is lower in energy than p, which is lower in energy than d. So you always have to go from low energy to high energy like this. All right. Now, if you're looking at this and saying, what are you talking about, Mr. Dion? You completely lost me. Well, electron configuration is something that you really have to try for yourself in order to master it. And so before you get intimidated by electron configuration, just stay with me a little bit longer here. It says the electron configuration for an element lists all of the electrons that occupy each shell, subshell, and orbital. So we're going to give the shell, the N, the subshell, S, P, or D, and then the orbital, we're going to say how many electrons are in those orbitals, okay? So subshells are written by increasing energy. So we're going to go, like I said, we go from N is equal to 1 to 2 to 3, okay? Then we have S is lowest energy, followed by P, followed by D, etc., etc. And the number of electrons in each subshell is indicated by a superscript. So like I said, an s orbital can hold a maximum of 2. A p orbital, there's 3 of them, so they can hold a maximum of 6. And d orbitals, there's 5 of those, and so we can have a maximum of 10. All right? So, for example, the proper electron configuration for carbon, which has an atomic number of 6, is 1s2, 2s2, 2p2, right? Because carbon has an atomic number of 6. Remember that atomic number is the number of protons, right? But remember that carbon, if it's not an ion, it's a neutral atom. So that means it's going to have the same number of electrons in this specific case. The number of protons and the number of electrons will be equal. And so if you tally up the total number of electrons in this electron configuration, we have 1, 2, 3, 4, 5, 6. Okay, cool. So there's just one thing I want to share with you here, which is there are some things you have to kind of learn about electron configuration. And that is, you can see that energy is increasing in this direction, right? Increasing energy. So we start with a 1s, then we go to a 2s, then a 2p, then a 3s, then a 3p. But the thing is, we don't go directly from a 3p to a 3d and then a 4s. You can see the 4s is actually stuck in between the 3p and the 3d. And if you're like, well, how am I going to remember that? I'll show you how to do it using the periodic table. And you're always going to have a periodic table at your disposal during your exams and if you're doing your homework. So there's a pretty straightforward way to remember this. But the reason why the 4s is lower energy than the 3d is due to something called orbital mixing, which we don't cover in this class. But it is a trend you do have to know. So, subshells in the periodic table. Remember, we have our shell, which is our N number, right? N is equal to 1, 2, or 3. The subshells are the S, P, and D, okay? Now, it turns out that the periodic table can be broken up into blocks on the basis of the type of subshell the electrons are placed into as we proceed through them in order of increasing energy. So check this out. You want to pay very close attention to this slide, okay? First of all, you'll notice that the first 2 groups, look at this, the first 2 groups are called the S area. I like to call it the S block, okay? That's what I was raised calling it, okay? Is the S block, and you'll notice that helium actually belongs over in the S block. It actually belongs up here, okay? And there's good reasons for that. which I'm not going to get into the whole detail of that for now. But again, you can treat helium as if it's over here because helium can only have electrons in an s orbital, okay? Then, okay, I'll just erase that, okay? Then we have the p block or the p area, which is over here. And again, I like to call it the p block, and that's everything that's in green. And then down below here, we have the d area. So this is what I call the d block, which is where the transition metals are over here like this. So if we think about an element like carbon, which we had the electron configuration written out on the previous slide, carbon is right here, okay? It's element number 6. So you have to start with the lowest energy electrons when you're writing out your electron configuration. So where do the 6 electrons in carbon come from? Well, we have to start at the beginning, always. So we're going to start with 1, 2, 3, 4, 5, 6. Those are the 6 electrons. So where's the first? So if I'm talking about this electron right here, where's the first electron? It's in n is equal to 1, and that is why they put 1s, right? Because this electron is the first electron. It's n is equal to 1, and it's in the s block, so we have 1s. But hydrogen only has 1 electron, and we need 1, 2, so we have 1s2. But remember, there's only one type of s orbital, and it can hold 2 electrons. So then, what comes after helium is lithium, where n is equal to 2. So we're going to put 2. Remember, we're in the s block for lithium and beryllium, so we're going to go 2s2. So far, we've accounted for 1, 2, 3, 4 electrons. But remember, carbon has 6. So then we're going to go over here, and we're still in n is equal to 2, right? This is still n is equal to 2. Look, if you just draw a straight line, let me get my ruler out here. Okay, just draw a straight line. You can see you're still in n is equal to 2, okay? So then we have 2p, 1, 2. So we're going to put here 2p2. And so that would be the electron configuration for carbon. So you saw on the previous slide that after the 3p, we went to a 4s and then to the 3d. So the way you can remember that is that for your p block, the numbering of the n's is going to be the exact same as your s block. So look, it's going to be n is equal to 2, 3, 4, 5, 6, 7. The exact same as here. But for your d block, there's an exception, okay? For the d block, your n, and there's not enough room here, but your n, let me get a blue pen here. Your n is actually going to be equal to 3, 4, 5, 6. So you see how it drops down by 1. So you go from a 4s to a 3d and then up to a 4p, okay? So that's how you're going to remember that. So again, you can always scribble this on your periodic table when you're working, when you're practicing your electron configurations. So elements that occupy the same group or column, right, the same family in the periodic table, they're going to have similar electron configurations. And this pattern helps us explain why elements in the same group display similar properties. Remember, elements in the same group or the same family are going to react similarly, or they're going to have the similar properties, and that's because their electrons are organized in a similar way. So you can see here we've got lithium, sodium, potassium, rubidium. If we go back here, you see those elements are here. Lithium, sodium, potassium, rubidium. They're all in group 1 or family 1. Well, look at their electron configurations. They all end with S1, 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 right? It increases from 2 to 3 to 4 to 5, right? So lithium ends with 2s1, sodium ends with 3s1, potassium ends with 4s1, and rubidium ends with 5s1. But the take-home message is that they all have one electron by itself in an s orbital in the highest energy orbital. And so that's why they're all going to react similarly. And those electrons that are found in the highest energy orbitals, we call those valence electrons. And so you can see that each one of these elements, lithium, sodium, potassium, rubidium, they're all in the same family. They're all in group 1, okay? And they all have one valence electron. So they're all going to react similarly because they all have that one valence electron. Now, if you're thinking, well, what if I'm looking at an element that has a lot of electrons, then I'm going to have to write out this big long electron configuration. Well, I would say, yeah, you will. Okay, that's part of life. Okay, but there is a shorthand configuration which we can use, which is what we call the noble gas configuration, which is an abbreviated form of electron configuration. And the way that you do a noble gas electron configuration is what you do is you take your electron configuration. So you see sodium is 1s2, 2s2, 2p6, 3s1. What you do is you look for the noble gas that precedes the element. So precedes means comes before. So let's go up to sodium. So a lot of jumping around here. Maybe I should clear some of my table here. Just delete all that. Okay, so if I look at sodium, okay, sodium is here, element number 11. Maybe I should use a different colored pen here. So sodium has 11 electrons, right? So we start with n is equal to 1, 1s2. Then we go over to n is equal to 2, 2s2. That's only 4 electrons. Sodium has 11, so we've got a few to go. Then we go over to n is equal to 2, but now we're in the p block. So we've got 2p, 1, 2, 3, 4, 5, 6. So we've got 2p6. And then we come down to 3s1. Okay, good, 3s1. But for the noble gas electron configuration, the shorthand, what we do is we look for the noble gas that precedes, comes before sodium. Well, you would remember that group 18, these are the noble gases. Noble gases. So what's the noble gas that comes before sodium? It's neon. And neon has 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of this part here, that's the electron configuration of neon. And so the shorthand is going to look like this. We'll just put sodium is actually neon, and we'll put it in square brackets like this, and then we'll just write 3s1. So this part takes care of all of this, and then we just have to put our valence electrons. And there you go. That's how you write an abbreviated or the shorthand or the noble gas electron configuration. And so we can save some energy there. The students will sometimes raise their hand in the in-person lecture and say, Mr. Dion, do I have to know how to do both? And the answer is absolutely you have to know how to do both. So all chemistry students and instructors alike, we all have to know how to write out the long form of an electron configuration as well as the shorthand of an electron configuration. All right, let's take a look at an example. Arsenic, oh boy, is known for its toxicity and may play a role in the development of a number of serious conditions. For arsenic, provide the full electron configuration and the abbreviated electron configuration. So you can see here they've shown you some of the early life health effects of arsenic poisoning, and then some of the later ones too. So arsenic's pretty dangerous. But anyhow, let's see if we can come up with an electron configuration for arsenic. Now I'm going to have to go back to my periodic table slide just so we have that as a reference. So just bear with me. I'm going to scroll back here, and we're going to find arsenic on the periodic table. And I recommend, working on the names of the elements. I recommend reading the periodic table once a day, okay? Just so you familiarize yourself with the names of all the elements. And arsenic is here. It's element number 33. And so for arsenic, maybe I'll use my black pen. Arsenic has 33 electrons. So we're going to start here at n is equal to 1. So we're going to do 1s2. So that takes care of these two. Then I'm going to go 2s1, 2. So I've got 2s2. We got 33 electrons. We've covered 4 of them. So we've got 29 left. All right, so let's keep moving here. So then we go to 2p. Remember, this is the p block or p area. 2p1, 2, 3, 4, 5, 6. 2p6. Remember, the p orbitals can hold a maximum of 6 electrons. So now we're full. So now we go down to 3s1, 3s2. So we've got 3s2. Now remember, I said we go from 3 over here to 3p. So then we go 3p1, 2, 3, 4, 5, 6. So 3p6. Still not there. Still got a ways to go. Then we go to 4s1, 4s2. So 4s2. Then after that, remember, I said that the n drops by 1. So we have n is equal to 3, 4, 5, 6. So we have n is equal to 3. We have 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10. Then we come back up to n is equal to 1. So 2, 3, 4, 5, 6, 7. So we have n is equal to 4p 1, 2, 3. So 4p3, like that. So that's our full electron configuration. Now, if we want to write out the, if we want to put in the noble gas electron configuration, we just look for the noble gas that precedes or comes before arsenic. And if you go backwards, 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 you come up to argon. Argon is the noble gas that precedes arsenic. So we're going to put here argon. I'd tell you a chemistry joke, but all the good ones are gone. All right, so you can see that argon goes up to 3p6. So all of this here is covered by argon. So then we're just going to write the remainder, which is 4s2, 3d10, 4p3. There we go. And so you can see the solution is exactly what we came up with. The full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Then for the noble gas electron configuration, remember the argon is covered by everything up to the 3p6. So our noble gas configuration is going to be argon, and then we just put the rest, which is 4s2, 3d10, 4p3.